Okay, so the question is, what is the origin of life? I mean, how did life actually begin? Or more specifically, how did prokaryotic life begin? Because we already know how eukaryotics, came about. They came about from prokaryotes. So, but what about the prokaryotes? Now, this is sort of a wrap around it in your mind type thing, where they call it the biogenesis paradox, in which we know for a long time they thought spontaneous generation, which is the emergence of living things from non-living things, was a lot of people accepted it back then, and it wasn't until Louis Pasteur did his famous experiment with the gooseneck bottles that showed that it wasn't living from non-living, it was some sort of microorganism that allowed there to be growth in these right here, in these flasks. So, how did this life arise then? If all life comes from pre-existing life, which is what they call biogenesis, then the first organism had to arise from another living organism and therefore cannot be the first living organism. Do you see the paradox now? But life on Earth was different back then. That's the thing to remember, is that life on Earth now the environment now is completely different from the environment before. In early Earth, you have a lot of violent catastrophes happening. There are extreme weather changes, Pangeas breaking and reforming. And so you have a lot of these environmental factors that are at the extremes. And so it's really hard to classify what is living and non-living based on, just like postulations and stuff. So they say that life on Earth back then was completely different than it is now. There wasn't oxygen. The energy sources are more extreme because you have volcanic eruptions. You have no ozone in the atmosphere because there's not any oxygen yet, so the sun is beating down profusely. So perhaps young Earth could have supported the notion of spontaneous generation, but not in the sense that we're using it today with Louis Pasteur. Perhaps there is sort of a transformation from non-living into living by chance, or over millions and millions of years. So the one of the hypotheses that they have come up with, which is completely testable, is that maybe abiotic factors somehow rearrange themselves molecularly to become biotic factors. And it sounds like science fiction, but they've actually done studies, and they've done experiments on this. And so it comes in four stages, this hypothesis about the origin of life. The first stage, abiotic synthesis of small organic molecules comes about. All right, so this would include amino acids and nucleotides. And then the monomers of these abiotic organic molecules join to make polymers, which would be proteins, nucleic acids, things like that. And then somehow they gain the ability to self-replicate, to make inheritance possible. And then somehow they package themselves into these protobionts with a membrane and a stable internal environment that can sustain themselves, regardless of the outside environment. So all four of these stages have to be testable, and they are. They actually have scientists who have gone about and tested them. So the first one, which was really famous, is called the Miller-Urey experiment. Okay, this is talking about, can organic molecules really come from inorganic molecules, from an inorganic environment? Early Earth's atmosphere favored the synthesis of organic molecules from inorganic material. Why? Today, our atmosphere is too oxidizing, which means that we have too many free radicals like oxygen and ozone by themselves that inhibit the synthesis of any kind of molecule. Normally, it's the breaking down, which is what we see today. So these organic molecules then need to be synthesized. How do they get synthesized? Well, today we know that enzymes or proteins synthesize them, and they lower the amount of activation energy that you need to make that reaction occur. Well, back in early Earth, you have an abundance of energy. I mean, you've got the sun, you've got UV, you've got lightning, you've got heat from volcanic eruptions. And so the activation energy counts for nothing because you have an abundance of all this energy. And the lack of ozone makes the sunlight just immensely intense. And so the conditions back then actually do favor organic synthesis from inorganic molecules. So Miller-Urey were actually going to test this. And so they recreated Earth's primitive atmosphere in this little contraption right here. And they actually found that when they add all of these inorganic molecules, that the contraption will actually produce a variety of amino acids and other organic compounds. So that's the first stage that they've tested. Now the second stage that they've tested is going to be the polymerization of these organic molecules without any enzymes. All right, so we talked about forming organic molecules from inorganic compounds, right? You have an abundance of energy, so enzymes count for nothing. Well, in the case of monomers into polymers, you need enzymes to do that, but back then you have such an abundance of energy that you don't really need you don't need enzymes right now because it doesn't matter. So they believe that, with the sun, with the intensity of the sun, it heats up Earth, so you have hot sand, clay, rock. These all heat up to such a high temperature that it spontaneously polymerizes these monomers into polymers. And so you see this a lot with, volcanic activity is very high back then. You have these deep thermal vents where all of these bacteria have been found to live. And so it makes sense that if you have a whole lot of energy, you don't really need enzymes because activation energy doesn't mean anything. And they've also tested this as well. Now, third one is that you are able to replicate. You can form self-replicating molecules. Now, we've always said that the central dogma is it's DNA to RNA to protein. And they've actually postulated that back then in the early Earth, it's an RNA world. Right? Replication happens via RNA. And the reason why they believe this is true is that RNA has been found to not only serve as a genetic information carrier, but it also serves as an enzyme. And we've seen this, we know this now by looking at ribozymes, okay, which are found in our RNA. Ribozymes have actually been, if you guys remember, they've been found to help remove introns. They help to synthesize ribosomal RNA, messenger RNA, and tRNA, and they're autocatalytic, which means that they can cleave themselves. So it makes sense then if an RNA molecule can act both as a genetic carrier and as an enzyme, whereas DNA only acts as a genetic carrier, that it is more useful in the development and the evolution of self-replicating molecules. So, one of the other arguments that they give for this is that single-stranded RNA is more diverse in its 3D conformation than double-stranded. Double-stranded has to be in a helical type manner. And so you have to see that single-stranded RNA can fold into different types of molecular shapes and conformations. It's more stable and it replicates faster than double-stranded DNA will. Now, with all things, natural selection works on everything, living and non-living. So they say that the same thing applies with RNA. In the RNA world, sequences that have the ability to replicate faster and acquire more monomers to replicate themselves are going to prevail, all right? Just like the organisms that can produce more offspring and can produce more offspring in abundance and live longer to produce more offspring are going to prevail. So this means that the RNA sequences that can replicate faster or acquire more monomers more easily are going to be the ones that are going to survive more often. And with occasional copying errors, which always happen, you get mutation in everything. Sometimes this actually enhances the sequence, creating this kind of like family of closely related sequences that prevail. And so they say then that once you have a self-replicating molecule, you can form what is called a protobiont. And this is like a precursor to a living thing. So it's an aggregate of all of these abiotically produced molecules that become the ancestors to organic living molecules. And so they exhibit some properties of life, but they can't replicate. All right, so what they mean by that is that liposomes, which is the example they give you, are not living, but they display some properties of life by, they can come together to form lipid bilayers. And so they kind of verge on the not really living, but they have the potential to be living, so they will go in the direction of living. And so they assume then that the natural sequence of this is that RNA is going to start packing itself into these genes that are in these protobiont units. And they eventually will start to accumulate enough abiotic factors in such a manner that they can self-replicate and sustain themselves in an internal environment that now they've transformed themselves from abiotic into biotic. All right, so everything is always in a competition. The struggle for existence doesn't just apply to just animals. It applies to everything on Earth. So an RNA sequence, all right, with some sort of gene sequencing or folding that favors an environment is kept as a unit in a protobiont because it's favorable. Both the RNA and the protobiont are more successful and they leave more offspring because now they can self-replicate. Mutations help to vary a gene within a protobiont family without actually, some of it's detrimental, but some of it is actually favorable. And this is what we call evolution on the molecular level, right? There is evolution on every single level. But this eventually leads to DNA replacing RNA because DNA is more it's more stable as a repository for genetic information, whereas RNA in single-stranded is kind of not as stable as it should be in double-stranded DNA. And then RNA, after it is replaced with DNA, is free to take on that role as the intermediate between genetic material, which is DNA, and the protein enzymatic material, because it does both, right? It makes sense because RNA could have been was the genetic material for a very long time. It also had enzymatic capabilities. So it makes sense that it now becomes the transcription translation between DNA and proteins, right? Hence you get your DNA, RNA, protein central dogma.